Welcome back. So hopefully you had a chance to think about that whiteboard exercise, and hopefully you found that the integral of psi 1 star times psi 2 dx is 0. I'm going to cut now to a picture that I drew that shows this, that shows that the total area under the graph of these, the product of these two stationary states vanishes. So, to sum up orthogonality, we can say that stationary states psi sub m and psi sub n are orthogonal in the following way. If I calculate their inner product like this, I get 1 if m equals n. So if I have the same stationary state, otherwise I get 0. Now, this idea that my unit vectors, so my stationary states, are orthogonal, turns out to allow me to uniquely express any function between 0 that vanishes between 0 at 0 and L in terms of these stationary states, just like I can express any vector in terms of my basis vectors I hat, j hat, and k hat. Let me erase the board and elaborate. So, like I talked about earlier, I can always write any 3D vector in terms of my basis vectors I hat, j hat, and k hat. So I can always write, for some arbitrary vector A, I can write it as ax I hat plus bx, ax plus ay. We're talking about vector A here, plus a y j hat plus a z k hat. The same thing I can do with my infinite square well wave functions. So for any arbitrary wave function that can be in an infinite square well, so it has to vanish at 0 and L. So similarly, let me switch colors. Any wave function, so I'm going to use psi of x to denote any wave function. Oh, any I can write it as a sum. And now, because there's an infinite number of stationary states from n equals 1 up to n equals infinity, I have to write this sum as a sum from n equals 1 to infinity. There's an expansion coefficient that's sort of analogous to the components ax, ay, and aaz. I'm going to follow Townsend's notation and denote those coefficients with c sub n, and then I'll write this as my multiplying my stationary state psi sub n of x. So let me write out the first couple of terms of the summation to be really clear about what I mean. So I can always write this as c1 psi 1 plus c2 psi 2 plus c3 psi 3 plus dot dot dot. I think you get the idea there. And if I were to write out what my wave functions are explicitly, right, so I'll go back to using summation notation. So I can write this explicitly from n equals 1 to infinity in terms of Cn. Oops, little n. And then you know what the stationary state wave functions are. We worked this out last week. Properly normalized, they end up going like root 2 over L times sine n pi x over L. Now, this might just look like a bunch of stuff, but it's actually really, really cool. And it's really actually, it still blows my mind every time how you can build like completely arbitrary stuff out of adding up a whole bunch of sine functions. Now, this is something that you might recognize if you've maybe seen it in a math class. This, sort of the expansion of some sort of arbitrary function in terms here of sines, this is what in math we call a Fourier series. And if you take math methods next year, you will talk in much more detail about Fourier series and sort of a branch of math called Fourier analysis. But what I'm going to do now is I'm going to cut to my computer where I wrote a little bit of code to show you the power of this kind of expansion and how any arbitrary wave function can be expanded in this way. So, I just wanted to show everybody a computer simulation that I wrote to show you some examples of ways in which we can represent an arbitrary wave function in an infinite square well as a sum of the sinusoidal stationary states. So the first example I want to look at is what I'm calling a box wave function. So this is a wave function that's, so I've plotted it here. So it's flat inside the box, so between 0 and L, but it's 0 at the edges. So imagine, kind of like how I've plotted it here, that the wave function sort of very abruptly ramps up and then drops back to 0 down here. So you might be thinking, well, this box looks nothing like a bunch of sine functions. But so let's see what happens. So here's what I've got for this for n equals 1. So I'm plotting the series expansion, but stopping the summation at n equals 1. For n equals 1, right, we just have sine pi x over L, and in fact, right, this doesn't look anything like a box. But we start to do better if we increase the number of terms we include. So this is for going up to n equals 3. I'm going to tweak this argument here to show you as well the individual stationary states I'm adding up. So that's what you're seeing in the orange and the green here. It turns out for this particular wave function that all the even terms vanish. So okay, though this still doesn't look boxy at all, but let's see what happens if we keep dialing this up. So if I crank it up to 5, now we have 3 different things contributing. Maybe this is getting a little boxier. Let's crank this up to 11. Alright, so you can start to see how, okay, it's rippling here, but it's maybe we're starting to see a box emerge. Let me turn this up to 21. Okay, I think you can start to see that we're getting flatter and flatter. I'm gonna, again, you can see all the individual stationary states here. I had to calculate what the right coefficients were. And I'm going to turn off the individual plotting since it's getting a little messy. So here's 21 again. We can keep dialing this up, so if I now turn this up to 51, we're now getting something that's sort of flatter and flatter in the middle, okay, and we've got more and more of a sharp edge at 0 and L, right? But now we still have some sort of ringing here at the edges, but we can try to keep cranking on this. So if I go up to 101 turns, right, again, we still have some ringing, but we're getting flatter and flatter. Now, we can keep going, so let me increase this to 201 Nmax. Again, you can already see this is starting to look quite a bit flatter in the middle. Again, still a little bit of ringing at the edges, but we're doing better and better. And now if I crank this up to 500, so again, aside from something at some ringing at the very edges, we're doing actually very well in getting something that's flat in the middle. And so that is an example of how you can build up something, even something quite sort of not sine-like this box, out of adding up sines. So that's the idea of a Fourier series, or in the quantum context, if this were to represent some arbitrary wave function in an infinite square well, this would be the beginning of the expansion of that wave function as a sum of stationary states. Let me show you one more example so that you can see what the whole point is. You're actually going to work with this particular wave function in the homework for this week. It's the last problem. So this is what I call a tent wave function. It's piecewise defined, so it sort of shoots up and then drops back down linearly, so it looks like a tent. Once again, we can go and plot the summation of this in terms of the stationary states. You will go, and the last question for this week's homework is to calculate what those expansion coefficients are. So think of this as sort of a preview of Friday's homework. So let's start off with just n equals 1, and there's sort of nothing interesting to see with the individual. So once again, right, for n equals 1, we have sine pi x over L. This doesn't really look like the tent we started off with. But we get better as we increase the number of terms once again. So let me plot the individual terms here. So here's sine n pi x over L, sine 3 pi x over L in green, and the sum is bright blue. Still not very peaky, but we're getting maybe a little bit closer. Let me crank this up to 7. So okay, you can sort of see how this is going. We're getting maybe a little bit flatter on the edges here, and so let's crank this up to 20. I'll take a jump up to 21. All right, we're getting flatter and flatter and flatter over here, and more peaked there. I'll now take the maximum number of terms up to some larger number. So let me go up to 51, and I'll stop plotting the individual ones so the graph doesn't get too cluttered. And now for taking that summation up to n max equals 51, we're starting to get something that looks more and more peaked. And if we keep on doing this, so let me turn this up to 101, right? This is now starting already to look pretty good, right? If I take this up to 201, right, you've got that. And by the time I take this up to like 501 maximum number of terms, right now you'd be hard pressed to sort of by eye see that there's much of a difference between our original wave function here and the result of summing up the stationary states up to n max equals 501. So this is a topic that you're being introduced to now, so Fourier series, which you'll continue to discuss in, whoops, my bad. So this is a topic that you're being introduced to now, the concept of a Fourier series mathematically, or in physics terms, that any wave function can be written as a sum of stationary states. You'll continue to discuss ideas like this in more advanced classes. But now what I want to turn our attention to is the problem of how do I calculate what the expansion coefficients are for some particular initial wave function. So in other words, how did I know how much of the different sine functions to add up in the simulation I just showed you? The next thing that I want to talk about is finding the coefficients in the expansion. Because none of this is any good if we don't have a way to calculate what the expansion coefficients are, or in this analogy, what the x, y, and z components of some arbitrary vector A are. So, formally, how could one find the x component of this vector A. It works, it can be done in the following way. So can find my sort of expansion coefficient A sub x, the x component, using, right, I hat dot A. So if I just dot my unit vector I hat with my vector, so if A, right, if I have I hat dot some arbitrary AX I hat plus A Y J hat plus A Z K hat, right, my dot product is distributive, right? So I can distribute my dot product in all three of these terms. Now, here's the important thing about orthogonality. If I have I hat dot I hat, right, I get 1. So this gives me A sub x from this first term. But because my I hat is orthogonal to j hat, when I do the dot product of I hat with this term, I have I hat dot j hat gives me 0. So I have ax plus 0. Same thing applies to I hat dot k hat, because those are orthogonal. Right? So I end up with just A sub x. Similarly, right, I can find my y and z components in the same way. You can convince yourself that j hat dot a hat will pick out my y component here, and similarly for the z component, a sub z equals k hat dot a. Now for vectors in 3D, this is not so hard to sort of see because sort of the orthogonality is kind of like obvious. But the same thing applies to infinite square well wave functions, even if the math is a little bit more cumbersome. And I'm not going to go through it in gory detail, but I'll say the result. So similarly, right, I'm going to end up finding my coefficients c sub n by taking an inner product with the between psi and the appropriate sort of analog to a unit vector or my basis vector. Taking an inner product with like stationary state psi sub n. So it turns out to be the integral from 0 to L of psi n star of x psi at psi subplane psi of x. So this is my arbitrary wave function here. So let me unpack this. This is a really important equation, so I'm going to box it. Okay. So this is my expansion coefficient. This psi of x is my arbitrary wave function. And then my psi sub n star, this is my basis function, this is my stationary state. And so this is the nth stationary state, and this is the nth expansion coefficient. So this is my basis vector. And right, so again, hopefully you can see the parallel, right? So for my component, so here, or my expansion coefficient, that's analogous to that. And then so I have a dot product here and my inner product over here, And what I always have is I have my my basis vector, right? So here my unit vector, here my stationary state, being inner producted or dot producted with my arbitrary vector here, my arbitrary wave function there. So, what I want to close today with is an example where you can go and calculate one of these expansion coefficients for a particular wave function. Okay, so let's wrap up by looking at this example where I'm asking you to find the C1 expansion coefficient for this wave function here. And it's a flat wave function, right, as we saw earlier. It's sort of flat between 0 and L, but we should think of this as just sort of dropping off to 0 really quickly right at 0 and L. So, right, the C1 expansion coefficient, as we've seen, is going to be given by the integral from 0 to L of my psi 1 of x star. And here my stationary state is real, so I don't have to worry about the complex conjugation, times my arbitrary wave function psi of x dx, right? So let's do this. Since I don't have to worry about complex conjugation, I can just put in root 2 over L. This will go like sine pi x over L. My arbitrary wave function is just going to give me a factor of 1 over root L, and I have to integrate this dx. Now, there's only one thing that depends on x here, and that's my sine. So I'm going to pull out all of this stuff. So I pull out a root 2. I have two factors of square root L in the denominator, so that turns to an L. Right, and so I have 0 to L sine pi x over L dx. And you can probably think about how to integrate sine. So that's going to give me root 2 over L. So I'm going to get I'm going to have a minus cosine here. And because if I think about differentiating this, I have a chain rule. I have also a factor of L over pi to think about, and I need to evaluate this from L to 0, so I can check if I differentiate this. Derivative of cosine would be minus sine, so I have this minus sign here to give me sine, and then chain rule pulls down a pi over L, which cancels that factor of pi over L. If you want to be sort of more careful about this, you could also solve this by making a u substitution, probably with u equals pi x over L. Alright, so what's left for me is just to evaluate this. So I get C1 that equals root 2 over L. For the first term I have minus, so if I plug in L here, I have actually, before I do that, let me factor out the L over pi. So now I have minus cosine pi L over L. And then minus this whole thing evaluated at 0, which is a plus cosine 0. Now you know that cosine 0 is equal to 1, so let me just simplify this. I have my L's canceling here, so I end up with a root 2 over pi. Let me do the positive term first. I have cosine 0 equals 1 minus cosine of pi, which is minus 1. So 1 minus 1 gives me 2. So I end up with C1 equals 2 root 2 over pi. So today we've seen a really powerful analogy between vectors in R3 and wave functions in an infinite square well. Armed with these tools, next time we'll be able to definitively answer the question, what happens to an arbitrary initial wave function? We'll also be able to say more about the physical significance of these expansion coefficients like the C1 I calculated here. I'm going to end now with a slide that sort of summarizes the analogy between vectors in 3D space and wave functions. So I'm sure you'll have questions about this, so please feel free to ask away. I'll try to respond to as many questions as I can over email or Zoom or however is easiest for you. And I look forward to seeing you all. So we'll have class on Friday. We'll have a recitation on Thursday where we do some problems calculating some stuff with infinite square well stationary states. So see you then.